All right, good evening, everyone. Tonight, I'm going to teach you how to count. Uh, okay, I'm assuming you already know how to count. So really what we're going to do here is learn how to count things that have lots and lots of outcomes that you can't count by counting on your fingers or toes. Unless you have about 4 million toes, which I'm guessing you don't. But what do you do in those situations? Well, let's learn about some new functions that will help you count up lots and lots and lots of outcomes. Okay, um, so let's start off with a simple example. Suppose you have 4 pairs of pants, 7 shirts, and 3 pairs of shoes. How many outfits could you make? Keeping in mind that most of them probably look pretty horrible. Well, let's see, for every pair of pants, you can match one of 7 shirts, right? So if you were to make a chart, you'd have, 4 pairs of pants, and then for each pants, you'd have 7 shirts. So if you make a chart, it looks like you're going to have a nice little rectangle. So that would be 4 times 7. And then, so that's 28. So you have 28 pairs of pants matching with shirts. But now for each one of these outfits that you can make here, you're going to have one of 3 pairs of shoes. So outfit 1, 1, 2, 3, outfit 2, 1, 2, 3, outfit 3, 1, 2, 3. So it looks like you're going to multiply by 3 as well. And so the final outcome is 84 outfits. Now, again, most of those are probably not going to actually match colors. And of those 84 outfits, there's, depending on what colors and what patterns match, you probably make maybe a dozen outfits at the most. All right, so this leads to a very important principle, the basic counting law. Sometimes this is also called the fundamental theorem of counting. If you have tasks that can perform, you have a task that's performed m different ways and a second task that's performed n ways, then you can multiply those ways together to find the likelihood or to find the number of orders that you can get for those tasks. So this was the same thing as before. If I have um, 5 different ways to do the first task and 6 different ways to do the second task, then I have a total of 30 different ways. Now, this, of course, one big assumption here, and we're going to assume that you are not the imposter. Saz. Hmm. Okay, I had to go. I had to joke about that. Performing tasks. Anyway, um, if this video is in the future and the game has long since disappeared, this was from a video game called Among Us. Um, who knows? It was such a huge fad back in like 2019 that it may fizzle out and this video may live on after it. Anyway, kind of funny. Anyway, I had to do that. So let's see how that kind of works out. We're just going to jump right into kind of a few examples of where you can use this counting principle. First, in ways that are easily separated, and then others where it may not be. Okay, so when you're looking at pants and shirts and shoes, each one is a different group, and you're picking from completely different groups. So it doesn't matter whether you pick the shirt first or the shoes first or the shirt or the pants first or whatever. You're going to have 84 outcomes. Now, the Connecticut State Lottery or just any situation here where you have to select, items from a container, and each task is picking from the same container, generally without replacement. Um, so the Connecticut Lottery selects 6 random numbers from 1 to 44. Um, Other states have a lottery system very similar to this um, with different amounts of balls. Connecticut happens to be one of the states with the least amount of balls. Connecticut and I want to say Virginia have a lottery system where you pick from the numbers from 1 to 44. Others it's higher. Um, like I know Powerball is 69 numbers. Um, Mega Millions is something like that, 50 something numbers. So it's it's a huge, much larger amount of numbers. So this one is um, by comparison a little bit more accessible. So the numbers are drawn from 1 to 44, and there's 6 random numbers. So it's like there's 6 different tasks. So we have to think about what are the outcomes for each individual task. Okay, let's start with the first ball. Okay, so we're going to do, in this case, we're going to put our 6 selections down at the bottom. Oops, my pen turned off. So we're going to put 6 selections, 3, 4, 5, 6. We're going to put 6 selections at the bottom. Okay, now each one of these can be a different number, and they have to all be different from 1 to 44. So how many outcomes are there? So for the first one, we have 44 different outcomes. It could be any number from 1 to 44. Now, for the second ball, how many outcomes are there? Now, you may wonder, well, it depends on what's happening with the first ball, but not so. If one ball is selected, it does not matter what ball gets selected first. There's going to be 43 left in the chamber. And so we are going to pick 43 balls for the second choice. For the third choice, 42. Then for the fourth, it'd be 41, 40, and then for the last choice, there would be 39 balls left in the container. And we're not going to multiply any more than that because we're only making 6 selections. So once we've made our 6th selection, there are 38 balls left, but that does not matter. So we can pick essentially any 6 of these 44 numbers. So how many different things can happen? How many different groups can occur? Well, we'd have to multiply all of these numbers together. And that is a huge number when you go ahead and try to multiply that. So you get 44, 43, 42, 41, 40, 39. That is about 5.1 billion outcomes. So why do people play the lottery? That seems a bit excessive. 1 in 5 billion chance of winning? Because you can only win on one ticket. But here's the thing. In the Connecticut lottery, along with most other lotteries, you can choose the numbers in any order. So when the correct numbers are chosen, they're usually then ordered from smallest to largest, regardless of what order they were actually picked in. That means in your ticket, you can match the numbers in any order. And what generally happens is if you go to like a lottery retailer and you buy a ticket, they'll put the numbers, they'll select 6 random numbers, but then they'll put the numbers in order afterwards. Um, that's to ensure like it's an easy comparison, and it's a little bit easier to tell when you've made um, some matches. So it's reality, it's not this number because these numbers can then get shuffled. So then the question becomes, how many ways can this be reordered? All right. Well, let's let's think about this. So we have um, 6 different numbers here, and we want to think about how um, each one can go in specific spots. So let's say without loss of generality, okay, we're going to choose our 6 numbers for the lottery. And the numbers that come up are magically enough 1, 2, 3, 4, 5, and 6. So let's say those 6 numbers come up out of the lottery. All right. Now, we want to know because these numbers could really have been any numbers, right? Here's the thing. That these numbers could have come up, but the one could have come up first. It could have come up second. It could have come up third. It could have come up fourth or fifth or sixth. That one could have appeared in any position. Or that 2 could have appeared in any position. That 3 could have appeared in any position, right? Um, except, think about this. So you might think, well, 6 and 6 and 6 and 6 and 6 and 6. Except what you don't want to have happen is like if the 1 appears in the first position, then the 2 can't also appear in the first position, right? So each number has to go into an empty spot. So let's erase these, okay? And let's think about the number 1, okay? How many different spots can the number 1 go in? Well, it can go in one of 6 of these spots, right? So I'm going to just choose one, okay? I'm going to put a 1 here. So the 1 can go in 6 different spots. Now, assuming the 1 goes somewhere, where can the 2 go? Now, the 2, there's 5 available spots left, right? The 1's already here, so there's 5 available spots left for the 2. Now, you may ask yourself, well, can't the 2 also appear in the spot? Well, yes, it's equally likely for that 1 to have been anywhere else. And if the 1 were anywhere else, the 2 could have been here. We are accounting for that. So the next thing that we're going to look at, now what about the 3? Maybe we'll put the 3 here. There's 4 available spots. Now what about the 4? There was 3 spots. Now for 5, looks like there's 2 spots. And for the 6, there's only 1 spot left. The 6 has to go in the last open spot. Now we're going to multiply all this together, and that's 720. That means that these numbers can appear in 720 different orders, which means when we look at all 5 billion of these combinations, okay, that means that each possible ordering of each possible group of numbers is happening 720 times. So all I have to do is take this and divide by 720. And I get the number 7,059,052. That is the actual number of possible lottery tickets that can be generated. This is called counting with permutations and combinations. You are certainly not going to count all these tickets by hand, but now you know that there is just over 7 million possible lottery tickets. Now, what could you do with that information? I mean, yes, know that you have a 1 in 7 million chance of winning. Um, you could say get $7 million together and go and purchase 7 million lottery tickets and have a nearly certain chance of winning. Um, that would help if the jackpot were higher than 7 million, wouldn't it? It's almost like free money. That'd be easy. Well, you still have to go buy all the lottery tickets. You can't just walk into a convenience store and buy 7 million lottery tickets. Um, each store actually has a limit, believe it or not. So yeah, that's a lot of lottery tickets. If I recall now, I'm just pulling this, but I want to say each store has a limit. I remember seeing on the news that each store has a limit to how many tickets they can sell per day. Um, and I want to say something like 5,000 or 10,000. So if you were to buy 10,000 tickets at a convenience store in one day, you would then need to do that you need to do that in 700 different stores. Actually, in this case, you'd have to do that in 706 different stores in order to buy all the combination of lottery ticket. Yikes, it's a lot. That is a lot. Okay, here's another example of what we can do with counting. Um, Counting is not just for lottery tickets, but we can also look at interesting things that, where you have repeated patterns, and you might be interested to know like how many different things can occur. One copy of that is license plates. Um, Now, we don't use this format nowadays, but back when I was little, we had license plates of this form in Connecticut. There were 3 numbers followed by 3 letters. And in this particular format, you have numbers like, for example, you might have, 327 XJH, let's say. You'd have a combination like that. That might be a license plate or something along those lines. Now, I just pulled that out. That does not belongs to anybody I know. Um, I just pulled that random combination out. But yeah, so you have several things like that. So we want to know maybe how many license plates of this format exist. Um, Now, this is by no means an exhaustive list, and the true number of plates in this series is not really something I'd be able to figure out because there's a lot of exceptions. But we'll start with a few. Um, what you may not know is license plates are handed out in order. So like they start with 100 AAA, then 101 AAA, 102 AAA, 103 AAA, until it gets to 999 AAA. And then after that, they go back to 100, and then they increase the letter. They go AAB. So that's what they did starting in 1977. Um, and they went all the way through this. And they kept going until they reached the end of the alphabet. The last plate that they issued was 999CZX. That was the final plate of this series that they issued. And they made it all the way, and it took 35 years, which is kind of interesting. 35 years. Oh, hey, interesting. Why is it doing that? That's it. Hello. Why is it doing that? Oh, that's funny. Let's try that. Okay. Okay, so this is this is an oddity. I'm having a problem with my, there we go. Okay, so I don't know what was happening there. All right, so let's see. It took 35 years to go through all these combinations, and it seems like there'd be a lot of combinations. So let's figure out exactly how many there were. Okay, um, so here's a few things. Number one, plates never started with 0. The letters I and Q were never used. They look too much like ones and zeros, or Q looked like O from far away. Um, Letter combinations beginning with C, L, O, and V uh, were reserved for other uses. O actually was never used. Um, but O was used in the second and third positions. That's why I put it in this list. So C, L, O, and V were never used as the first letter, but they were used as the second and third letter. And they could be used there. So let's take a look at how many plates there were in this situation. All right, so we're going to make 6 numbers. 1, 2, 3, 4, 5, 6. 6 characters. Put a dotted line here. Okay, and now we had numbers and we had letters. So how many of each were here? So plates never started with a 0. Okay, so how many digits are there? 10, 0 through 9. But plates never started with 0. So there must be 9 combinations. No restrictions. 10, 10. So altogether, this is 900. That means there were 900 plates issued for each letter combination. So there were 900 AAA plates, 900 AAB plates, 900 AAC plates, and so on and so forth. All right, what about the letters? Now, how many letters were there? So the letters I, Q were never used. C, L, O, and V were reserved. 26 letters of the alphabet, only 20 of which were used here. Now the other ones, C, L, O, and V were being used, so that's 24 and 24 here as well. I and Q were never used in any position. Now all we have to do is multiply all that together. And we get 900 times 20 times 24 times 24. And that is 10,368,000. Okay, but we're not done yet because of the last piece of information. Last piece of information. ZZX, so nothing there, but ZZY and ZZZ were not allowed. So the thing is, like, why does that change anything here? And the answer is no, because This only pertains to the one case where you have two z's. So y and z were used many times as the last letter, but only the case of ZZY and ZZZ are ignored. But remember what we said before. We said before that each letter combination had 900 plates. So here's 900 plates, and then here's another 900 plates. So we're going to take this number and we're going to subtract 1,800. 10,366,200. And so that is the total number of license plates of this format. Now, again, that's a rough estimate. The true number is actually lower than that. And that's because there are several letter combinations, specific letter combinations that are used for other purposes. So, like for example, combinations like USA was used for certain types of America plates, like patriotic plates. PET was used for a vanity plate a special plate that you could order that like you donated money to animals. Um, and there's several other varieties of ones. There is, CAT, DOG, um, ones like that that were very specific to those. And there's lots of other ones. WOF is one, woof, that I remember. TLC was also used for pet plates. Um, oh, what else do I know? Oh, goodness. There's huge tons of them. PSU, there was a special plate for people who went to Penn State. Like, I don't know, there's all these combinations. So the true number of plates that were issued randomly is much actually lower than this number. Okay, that's just food for thought, not really important to the lesson, I suppose. But I guess that just goes to show you that we can estimate how many plates there were, but we don't really have a true number. Okay, so let's go back to now looking at the lottery problem one more time. We're going to look at the part where everything gets reordered. So in this particular case, I can ask you, let's say we have 5 students and they sit in a row of desks. How many different ways could those 5 students organize themselves? And you can imagine it's 120 because if you have 5 desks and you have 5 students, then those 5 students, the first student can go in 5 desks, and then another student now has 4 desks, and then another student has 3 desks, and then another student has 2 desks. The other thing you can think about the reverse too. In the first desk, you have 5 potential students. For the next desk, you have 4 potential students. For the next desk, you have 3 potential students. So there's a total, no matter how you look at it, of 120 different ways that you can order 5 objects. Okay. So this has an actual function, and it's called the factorial. So the factorial operation is an exclamation point. That doesn't mean we shout it. We're not going to suddenly be shouting "and" all over the place. Um, we just say n factorial. Um, and that word represents the product of all integers from 1 all the way down to n. So like for example, if I have say 7 factorial, that's equal to 7 times 6 times 5 times 4 times 3 times 2 times 1. Now you may wonder, like, do you really need the 1? Because multiplying by 1 doesn't change anything. No, you don't. However, the 1 is kept there for completeness sake because you're ordering 7 objects. And so you should have 7 factors. So the 1 is used for that last item that only has the 1 spot that it can go in. Now this is a big number. This is 5,040. Factorials get very high very quickly. For example, 10 factorial. is equal to 3,628,800. And then from there, every number that you're going to multiply, so 11 to get to 11 factorial, you're going to multiply by 11. And then you're going to multiply by 12 to get the next one, and then multiply by 13. And when you multiply by something larger than 10, it's actually gaining place values. So 12 factorial is a 9-digit number. 13 factorial is a 10-digit number. And the numbers get very large very quickly. One lovely thing about them, though, is that they have a massive amount of factors, um, simply because it's the product of so many different numbers. Okay, so the word permutation of a set of objects, a permutation, vocab term, is a specific ordering for a group of numbers. So, in other words, if I have 7 objects, there are 5,040 permutations. In other words, there are 5,040 ways to order those objects. Okay. Now, in the case of the lottery balls, though, we have more objects than the selections we need to make. We had 44 objects, but instead of ordering all 44 of them, we only had to order the first 6. We don't have to multiply all the way down to 1. We stop when we have made all selections. And so we have a function for this. It's called the permutation function. And so the function is a big letter P, not like probability notation. This is different. There's a little number n and a little number r that are on both sides of the P, and that is this. And so here we have r factors. So here's an example. Um, this formula is used when the exact ordering is important. So a good example of this one would be like if I have, say, 10p4. So 10p4 means I have 10 objects and I need to select 4 of them. So I'm going to do start at 10, and then I'm going to multiply by each number down until I reach 4 factors. So the reason for the 4 is I'm making 4 selections, but each time I make a selection, I'm 1 number less. I have 1 number less in the group that I'm looking at. So that becomes 10987. That becomes, oh goodness, if I can multiply that together, that's a pretty big number. Let's go ahead and do that. 10 times 9 times 8 times 7. Oops, I missed the 8. Oh, I didn't miss the 8, right. The 8 key is broken on my computer. 5,004. Oh, look, 5,040. Well, what do you know? A bit of a coincidence there. Okay, that does not always happen, folks. All right, so anyway, 5,040 possibilities. Now, this number is accurate if we need them in a specific order. An interesting case of this would be like if you're choosing people for named positions, like your student council, right? You have 10 people on student council, and you have 4 positions. You have president, you have vice president, you have a secretary, and you have the treasurer. Let's say you've got those 4 positions, and you want to know how many different possibilities there are. Well, considering that you're going to pick the people in order, so you have 10 choices for president, 9 choices for vice president, 8 choices for secretary, and then 7 choices for treasurer. And in that case, the order matters. So you can select the same 4 people out of the 10. But the ordering matters because it depends on what position they're put into. So in that case, it'd be 5,040 different possibilities. In practice, though, this is one of the few situations where order is actually important. In many cases, the order is not important. We just simply want to know, like, how many different possible groups that we can get. So in the case of lottery tickets, right, you only need to match the numbers in any order. So your job is to select the correct 6 numbers, order notwithstanding. Or if I need to get a group of people from class to do something and there's 15 kids in class and I need 3 students to do something, the order that I pick them doesn't matter. I'm just going to pick, 3 students. So like before, we had the numbers 1, 2, 3, 4, 5 on your ticket. How many different ways could they be arranged? Well, we have the notation for that now, 5 factorial. And that's 120 different ways. Um, for the 6 lottery tickets, 6 factorial, which is 720 ways. So when order doesn't matter, this is how many different ways that each of those exact orderings occur. So the numbers 1, 2, 3, 4, 5, if we were to make all the individual orders, those 5 numbers would appear together 120 times in each of their possible orders. On the lottery ticket, each group of numbers will appear 720 times. That makes this now what we call the combination formula. The combination formula is done, it's NCR, order irrelevant. And then here, order matters. So as we said before, in a permutation of objects is a specific ordering of them. A combination is a specific group or grouping. And so the grouping can happen in any order. So to convert order mattering to order not mattering, you divide by the factorial of the number of objects that you have. So in other words, going back to what we did before, um, the formula that we have now is to do this out. NPR is equal to n factorial divided by n minus r factorial. But now we're going to divide that by r as well. And so now we're going to have an extra r factorial in that denominator. So this is the formula that you use for NCR. The good news is you don't really need to use the formula too much because the calculator has an NCR function and an NPR function, and it has an exclamation point. Now, could you do this in the calculator by hand? Certainly. And I'll show you some quick ways of doing that too. But you also have a function to do this, and we'll look at the calculator in both ways. Okay, so let's see how this actually ends up being. So let's do an example of this. So if we have, let's say we have, I don't know, 8 objects. We have 8 objects, and of the 8 objects, I would like to choose 3 of them. Okay. So thinking about what we did before, okay? Um, we have 8 objects, right? So we're only choosing 3. So we're going to start at 8, and we're going to multiply by 7 and by 6, and we're going to stop because I only have 3 factors. We're going to divide by 3 factorial, or 3 times 2 times 1. So this is going to be 42 times 8. Actually, it doesn't matter because 3 times 2 times 1 is 6. That cancels out with that 6. That's equal to 56 combinations. So it turns out if I need to choose 3 from 8, so if I have a group of 8 people and I need to choose 3 of them, there's 56 possibilities for the 3 people I could end up with, assuming that the order does not matter. I'm just looking for what groups of 3 people could occur. 56 different groups. Using this factorial notation, what that ends up being is this. It ends up being 8 factorial over 3 factorial, 5 factorial. Knowing that the denominator, the 8 goes in the numerator, 3 goes in the denominator, and that 3 gets multiplied by the leftover 5. So 3 factorial that gets chosen by 5 factorial that does not get chosen. And we have that. And that always works. Again, as I said before, this is just kind of the technical part. There's a function on the calculator that does this for it. So let's turn this on, and we'll clear, and we'll go to, now wait a second, before we do this. The function that we're going to use is math. Go to the probability menu, and we're going to choose, there's NPR and NCR. Most of the time, we're going to use NCR. But keep in mind, this function is different than other functions in the calculator. This is not a parentheses function. You actually have to put this in after the number. That means, like, so you see how in this notation, how you have the 8 and then the C and then the 3. You're going to do the same thing in the calculator. So you'll have the 8, math, probability, NCR, 3. So you have to type in that number first in the calculator. You have to do that. 56. Okay. It's not a bad idea to put this in parentheses. The calculator will generally do NCR prior to doing other operations, but just to make sure it knows that, it's helpful to put it in parentheses. And we'll see a few examples of that. Okay. So now if I wanted to do the lottery, 44, math, NCR 6, 7,059,052. Perfect. What if I wanted to do some other ones like, if I have, we'll see some examples. Actually, let's go do some more examples. Okay. Let's say we got a class, right? Let's say we've got a class. I'm just going to choose one of my classes. Let's say there's 18 students in the class. And in those 18 students, let's say that there is 11 boys and 7 girls. Okay, now how many ways could I randomly select 5 boys? Okay, well, let's see, 5 boys, right? Now, if I'm going to randomly select 5 boys, now, regardless of whether I'm picking from just the boys or picking from everybody, we're not looking at probability, we're looking at how many ways. So I'm looking for 5 out of the 11 boys, right? So now, if they can occur in any order, 11, choose 5. I have a total of 11 boys, and I'm choosing 5. So the C stands for combinations, but also the C, because it also begins with choose. So the word choose kind of works here because we're choosing any 5 of those 11. And this equals to, oops, I'm pressing buttons here. And that's equal to, let's find out. I don't know that off the top of my head. 11, choose 5, 462. 462 ways. Now what about 5 girls? 7 girls in the class. 7 choose 5. This one I think I know more of the answer to. This one's a little bit easier to do. 21. So there are 21 different ways. Now, why is this one a lot smaller? Because we're choosing a larger proportion of the girls, so we have less amount that are out, that are not in the group. So it's an interesting way to think about it. Okay, so we can do this in lots of different ways. What if I wanted to what if I wanted to randomly select a different group? Let's say I wanted a sample of 4 boys and 3 girls. Now, the word and, of course, means multiply. So I want 4 boys, right? 11 choose 4. And then for 3 girls, I've got 7 choose 3. So 7 girls, and I chose 3 of them. And if I want all of this to happen together, how many possible groups can there be? Each group of boys can match up with each group of girls. So we multiply. And so in a calculator, I would do exactly that. Parentheses, 11, C4, parentheses, 7, and a C3. 11,550. Perfect. Um, and if you wanted to do these singly and multiply them together, you could totally do that too. Um, that works either way. All right, we are cooking along. Let's do a few more examples. Okay, how much time do I have here? Okay, this is a nice big lesson because this kind of covers 2 different things at once, like the introduction to counting and also like the applications of it. Okay, consider a standard 52 card deck. 5 cards are drawn at random. How many different combinations can be drawn that have 3 cards of one value and 2 cards of another value? Um, in poker terms, this is called full house. Well, let's think about this. 52 card deck, and we're pretty familiar with this point about a 52 card deck. So let's see. 3 cards of one value. All right. But the value could differ, right? So let's see. Let's think about it just with a particular case. So let's say we had, um, so the problem that we had on a mini quiz not that long ago involved kings and eights. So let's say we had kings and eights. Without loss of generality, let's say that, right? So we want 3 kings. So we want king, 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 ace, 8, or 8, 8. Okay, so let's say we want that, right? And so now we are going to do, well, I want 3. How many kings are there? There's 4 kings. So I want 3, but any 3 of the 4 kings. So 4, choose 3. So 4, choose 3. Okay, and that represents choosing the 3 kings. Now, how about the 8s? Now I'm 2 of the 8s, right? But again, how many 8s are there? 4. So choose 2 of the 4 8s. But now here's the thing. Did I say that it was kings and 8s? No. So how many different groups of values are there? There's 13. So of one value, there's 13 possibilities here. So 4 choose 3. Now that means there's that many ways, which happens to be 4. So there's 4 ways to choose 3 kings. But it may not be kings. It could be aces, twos, threes, fours, fives, six, seven. So what I'm going to do is, because it's any value, I'm going to multiply that by 13 to represent the fact that those 3 cards could be any value. But what about this? Now, my next question is, what about these? How many choices do I have for the other 2? Um, well, we've used one value here. I guess it'd have to be 12. Now the question is, can this be the same value as the kings? Like if I had 3 kings here, could I have another 2 kings here? No, I cannot. Why? Because there's only 4 kings. These could not all be the same suit or the same value. So there must be 13 possibilities for these three cards and 12 possibilities for those cards. So we multiply that. And so now we put it all together and we're going to multiply. And so that turns out that we have, uh, this ends up being 4. This ends up being 6. But you can do that in the calculator if you'd like. Um, and so what you end up with is 13 times 12 times 4 times 6. 3,744. There are 3,744 possible full houses. Okay, interesting. Okay, and you can do this to find out, like how many different counts that all the other different qualities of cards, like what's the likelihood of getting 2 pairs in 5 cards? What's the likelihood of getting, 4 of a kind, like all 4 of the same one? Like you can do all of those. And it's pretty fun to try to pull all that off. Okay. All right, next. Let's keep going. You have 9 red marbles, 6 green marbles, and 5 blue marbles in a jar. What is the probability that if you pick 3 random marbles, they are all the same color? Ooh, okay. Uh-oh, and now here's the thing. Now, folks, I'm asking for probability. Now I'm going to ask, so basically I'm looking for here probability 3 of the same color. So now what we need to do, remember that for probability requires us to have counts. We have to be able to count things. That's why we have to be able to do all the NPR, NCR notation first. So let's ignore probability and just count how many different things can happen. So we need, remember, probability. Probability is always a count of the successes over a count of the total. So we need to figure out how many successes, so how many times I can get 3 of the same, and I have to count how many possible things can occur. Okay. It's not as hard as it looks, as long as you can kind of see where the numbers are coming from. Okay, so probability of 3 of the same color. Well, we have red, we have green, and we have blue. So they must all be the same color. So it could be red or green or blue. And the word or, in terms of counting outcomes, if this can occur, or this can occur, or this can occur, if any one of them is okay, then we can simply add all those together. They won't overlap because you can't get both red and green at the same time because they all have to be the same color. So it's a straight addition and there's nothing to subtract, like nothing that's going to get counted twice. Okay, so what about, let's start with this, red marbles. How many red marbles are there? 9. We're picking 3 marbles. How many different ways could I pick 9 marbles? How many different ways could I pick 3 red marbles of the 9? So let's switch to red, and I'll write it out just to kind of color code it. 9, choose 3. So I'm picking any 3 of the red marbles. Those are how many successful events there are. It'd be 9 times 8 times 7 divided by 6. And so, whatever that comes out to be. So that's how many different groups of 3 red marbles there are. And any one of those groups is considered a successful outcome. Now, it could be green. Now we have 6 green marbles, right? And I could possibly have any 3 of the green marbles. And there are 5 blue marbles. So I could potentially have 3 of the 5 blue marbles. But we are picking 3, right? So the question then is, those are all the successful outcomes. It could be all 3 red, all 3 green, or all 3 blue. How many marbles are there? Well, we have 15 plus 5 is 20. And when I'm picking these marbles, I'm picking 3 marbles from the jar, but I'm picking the marbles and I'm reaching out. There's a total of 20 marbles, and I'm picking 3 out of the 20 marbles. So my total outcomes is 20 choose 3, the sum total of all of them. Um, so the idea being that, you know, I'm hoping that I get all 3 that are red, all 3 that are green, all 3 that are blue. Any one of those would suffice. So the total group of that is all of that put together. Out of literally anything can happen. So this 20 choose 3 represents any 3 out of the 20. So like a red and a green and a blue, or 2 blues and a red, or anything like that. So let's figure all that out. So 9 choose 3. So 9 choose 3. This is 84. Now 6 choose 3 would be 6 times 5 times 4 divided by 6. That's 20. And you can verify that, say if you want. So actually what you can do, easy enough, second enter, and then just go back and change that to a 6. Because you know what? That way we don't have to go back to the menu. And you'll find that that is, oh, bugger. Oh well, 6, math, NCR 3. Yeah, 20. Okay, and then 5 choose 3 would be 5 times 4 times 3. But it'd be divided by 3 factorial, so divided by 6. Um, and so that would be 10. So 5 NCR 3, 10. Okay, and that's going to be divided by 20 choose 3. So 20 choose 3 is 20 times 19 times 18 divided by 6. Not doing that one easily in my head. Although that's probably a pretty round number. So, oops. Again, be careful with that. You have to type in the first number. Okay, 20 choose 3. 1140. So what is the likelihood of this happening? Well, it would be 104 plus 10, so 114 divided by 100, 1,140, 10% on the dot. Kind of a lucky outcome there. Um, is it always going to be nice and even like that? No, but just kind of lucky the way it works out in this case. So just know where all the numbers come from. The 9, the 6, the 5, that's how many marbles of each color I have. I'm choosing 3, so I'm choosing 3 in each individual group. And the 20 is the total of all of them. Okay, hopefully that makes sense. We'll just do a couple more quick ones because it looks like this video is getting fairly long, but covers a few different sections. Suppose that there are 3 juniors in a class of 24 students. The rest are seniors. So let's see. So not terribly unlike the classes we have. What is the probability that if I randomly select 4 students, that I get at least 1 junior? Okay, here's this situation of the at least 1. That means I could possibly get 1 junior. or 2, or 3, or 4. Actually, can't do 4, only 3. Um, so you could think about the situation where there's one junior, two juniors, three juniors. Or remember, since you have all those different things, what don't you want to have happen? You don't want a case of 0 juniors. So at least one. An easy way to do that is 1 minus p of 0. So in other words, maybe what we can do is 1 minus the probability no juniors. Okay? So what's the probability that we get no juniors? Well, let's see. If we get no juniors, then we're selecting 4 out of seniors, right? And how many seniors are there? 21 seniors. So 21 seniors. And so if there's 21 seniors, then we're selecting 4 students. So, um, so 21 seniors would be 21, choose 4. Now, in this particular case here, it's out of what group? It's out of all of them, right? So the group of all of them is the 24 students. So it's 24 choose 4. So the probability that we get no juniors is equal to seniors out of everyone. And so it's 21 choose 4 divided by 24 choose 4. So this is a nice way that you can calculate this. And you know, we may have been able to do this problem before this unit too, right? So like you might have think, well, in each case, like what's the likelihood that the first one's a senior? 21 out of 24. What's the likelihood that the next one's a senior? 20 out of 23. Like we would have been able to do this before this lesson. Like this is a question you could have answered a few days ago, but the notation makes it a lot easier to work out. So now I can just figure this out. And so now all I have to do is go in the calculator and just do 1 minus parentheses. Um, Now in this case, it's probably a good idea to do 2 sets of parentheses. 21, choose 4, divided by parentheses 24, choose 4. And so you get 43.67%. 68. Okay. So the probability of no juniors is this. So 1 minus that. So clearly that gives us a 43.68% chance of getting at least one junior. Okay. Um, okay. So last one we'll do, and then we'll call it a day here. Um, Given a hand of 6 cards from a standard deck of cards, what's the probability of getting 3 fives and 3 queens? Okay. So same idea here, right? Um, Successes out of totals. And means multiply. So 3 fives. Now here it's a specific value, right? So 3 fives. So out of the fives, there's 4 fives, right? And we're getting 3 of them. 4 choose 3. Those are my fives. And 3 queens. Also 4 choose 3. Because any 3 of the 4 queens out of, now how many choices do I have altogether? I'm choosing 6 cards from the standard deck. Choose 6 from the standard deck of 52. So it's out of 52c6. As you can imagine, this is going to be a very low number. Now, in this case, 4s choose 3 happens to be um, 4, which makes sense because if you're getting 3 5s, then there's only 1 5 that's left out, and you have 4 choices for which 5 gets left out. So really, this ends up being, this is 4, that's 4. So it ends up being 16 over 52 choose 6. Very, very low, divided by parentheses 52 choose 6. 7 times 10 to the negative 7. Remember, you can move the decimal point back if you want. 0.0000070. Yowza, that's pretty low. Um, if you were to open this up to be 3 of any um, value and 3 of any other value, it gets a little better, but not by much. You're basically multiplying this by 132. Because, no, yeah, 132? No, 168. 13 times 12. No, 156. Anyway, you multiply by 13, multiply by 12. So you're not going to fare very well with this because 52c6 is a huge number. Um, it is, well, 44c6 was 7 million something, so 52c6 has to be even larger than that. In fact, I venture to guess 2.5 times. Well, you can do the math if you'd like. It's a big number. All right. There are a few other things that we can do here, but for the sake of time, I think that this is probably enough examples to see you through. If you need to use this lesson to kind of go back and review, you can certainly review these examples, okay? With all the proper explanations. Okay, folks, so I will leave it here. Have yourself a lovely evening, and I will see you in class.